So far we have been dealing with second-order differential equations that are linear and are homogeneous. So homogeneous means that we're going to have an expression like this with constant coefficients, by prime plus cy equals to 0. So this is what makes it homogeneous. The right-hand side of the equation is a 0, and we have learned that there is a way to find this by finding a characteristic equation and then finding the roots of that equation. And there are three cases for the different types of roots that we get that will give us a different solution. Now, what happens when this term here is actually not 0, but something else? So what happens if this term here is some function of x? So an arbitrary function of x that we choose. Well, we cannot really use the same method because now we have this term here. So things are going to get a little bit more complicated. So you might think, well, where would we actually encounter these types of differential equations? And I'll tell you, well, in physics and engineering, this is quite common. And I'm going to give you an example from mechanics, which I find it's a very visual example of this and will help you understand what is happening in a physical sense and why it is important to know how to solve these differential equations. So I'm going to have a very simple linear system. I'm going to have a mass, so a box on wheels, on a surface here. We're going to ignore the effects of friction or air drag or any other external factors, and we're going to attach a spring here. So that spring is going to have spring constant of K, and we're going to have a damper. So a damper is kind of like a spring, but it uses an internal fluid to absorb energy instead of just this coil thing. And this usually damping constant can be called C or many other things, but we're just going to call it C for this moment. And we're going to assume that the motion of the card is in the right direction. So that's going to be a function of x is a function of t, where t is the time. So as this card gets displaced, it is going to tend to oscillate back and forth because obviously the spring and the damper are going to be absorbing energy until all the energy has been dissipated from the system and it comes to rest. Now, what is the definition of this and why is it important? Well, if we consider the displacement of this car, so let's first of all draw the free body diagram, which is going to be the mass by itself. We're going to have a force here, which is not an external force, but rather the force of the cart moving in the x direction. That's going to be the inertial force. It's going to be a center of mass and the acceleration. And I'm going to use the notation x dot equals dx over dt. And x double dot is going to be dx over dt squared. So those are the first and second derivatives there. That's the notation I'm going to be using in this example. It's very convenient for mechanics. And on the other hand side, we're going to have two restoring forces. The first one is going to be kx, so that's the spring force. It's just the constant here times the displacement. And the damping force is actually dependent on the velocity of the cart. So that's going to be c times x dot. So now that we have our forces, we can find the sum of the forces in the x direction. And we know that the forces need to balance out. So they need to be equal to this. So mx double dot, that should be equal to these two forces. So they're going to be negative because they're pointing towards the left. So that's going to be kx minus cx dot. And now if we move these two terms to the left-hand side, we're going to be left with the equation mx double dot plus cx dot plus kx equals to 0. And if you notice something peculiar about this is that this is a second-order homogeneous differential equation with constant coefficients. So this is what we have been dealing with so far. So this is one simple application of this equation, how you would derive it and what solving it would actually lead to. If you solve this differential equation, you can actually find the displacement of the cart as a function of time, which is quite useful for analyzing dynamical systems and creating control routines and programming and all that if you're interested in doing anything related to mechanical or mechatronic design. Now, what happens with this type of equation? Well, it's very similar, but now the difference is that we're going to have to add, I'm going to make this eraser a little bit small so I can erase this properly. Now we're going to add an external force, and this is something we're going to call the driving force of the cart. So this is just going to be some function of t, and that's going to be pulling on it. So if we have the function of t here, and we're going to assume both of them are acting about the center of mass of the cart, then what's going to happen? Well, we're going to add that force here, and by moving the other terms to the other side, we're going to have mx double dot plus cx dot plus kx equals 2f as a function of t. And this driving force can be anything. It could be something like a sinusoidal or a trigonometric function. It could be sine of t or with some frequency there. It could be something like an exponential function, or it could have some value e to the alpha t, or it could be like a polynomial like t squared plus t minus 1. So this can be anything that we choose, and these are things that might be related to the force that it's acting on the system. So this is essentially how you would go about deriving that type of equation, and this is why we would need to solve it, because that driving force is actually going to affect the motion of our cart very, very rapidly, and it's going to cause a lot of unintended effects on it. So we need to investigate those if we are to design and analyze this system in a very efficient manner. Now, in the next video, I'm going to talk about, was more of an introduction to the concept of a non-homogeneous differential equation of second order. In the next video, I'm going to show you some examples of how to use a method called undetermined coefficients to actually solve equations of this type.